So welcome to another episode of, another meeting, and thank you for joining today. I'll be talking about meta-analysis, and this is something that I have actually learned later on in life, and I've always used comprehensive meta-analysis, the software, to perform analysis, and this is the first time I'm using Excel to show you the bits and bobs of the process. I've actually not used this methodology in any of the publications I have contributed to, so that's a fair warning. So before I start, I have to tell you that most of the work that goes into a meta-analysis is done prior to implementing the methodology. So whatever steps are required to create a systematic analysis forms the bulk of the work behind conducting a meta-analysis. So meta-analysis in itself is not a study. It is actually a statistical method. So here we are previewing this method with the assumption that we know what goes into conducting a systematic review. So you have your inclusion and exclusion criteria, very stringent, and then you have, your correlation matrix, and then, then you conduct some certain tests, and those tests tell you whether you should proceed with a meta-analysis or not. So, so the systematic review is something that actually contributes to the bulk of literature from which clinical evidence is derived. But meta-analysis is finding a strong foothold in, in the evidence synthesis world ever since the idea of network meta-analysis was introduced, which we are not going to cover today. I don't know how to do a network meta-analysis. So basically, here we are talking about, we will talk about a basic meta-analysis, which requires very stringent inclusion and exclusion and simple standardizations. For network meta-analysis, the inclusion-exclusion criteria is exhaustive. So you have more legroom to include more types of literature and more types of outcome estimates, and then you apply different standardizations according to your study needs. But that's for another day. So this methodology can give you an estimate of treatment effect from the studies that are only included in this analysis, not the treatment of treatment effect of that particular intervention necessarily. So we have to exercise caution while writing down our results and interpreting our results. So why should we conduct a meta-analysis? It enables us to combine data and summarize from multiple studies or clinical trials. So today's example, that I'm not using a clinical trial because not a lot of our faculty use clinical trials or do literature review on clinical trials. But anyway, so here we can combine multiple studies, and we gain statistical power by increasing the sample size, and also we get a single treatment effect from an intervention. And we also get evidence on the effectiveness of the intervention by combining studies which have unequivocal results, or they have problems with sample size. So they do not have enough strength of evidence in themselves, but when brought together, they can contribute to the overall evidence from that treatment. Meta-analysis can also be used to look at change in treatment effect over time. So this can only be applied to ratio and continuous outcomes. So when you have a range, for example, like gain in motion or reduction in tumor size, that's when you can use a meta-analysis to show that over time, this treatment might be unequivocal at time T1, but at time T2, this treatment has some effect. And the effect size can go up or go down over time, but you still get evidence on the treatment effect, a directionality to the treatment effect. And then, we come to the meat of the study, the meat of the presentation. So how do you conduct a meta-analysis? Before I jump onto this, do you have any questions? Okay, it sounds like you don't. So in order to conduct a meta-analysis, as I mentioned, you have to do a systematic review. Once you have the basic data in, so author, year, so that's a tagline for the study. So that's how you identify, that's a personal identifier for the study, if you will, in your data table. You have an outcome, and then you create an effect, then you deduce effect size, and the outcomes can be anything from odds ratios to rates, depending on what the outcome of your original study is. So here I'm talking with the assumption that you have only included studies in your study which require the inclusion, which has an inclusion criteria, stringent inclusion criteria in the outcomes. So all the outcomes in all the studies you have included has to be the same, and the treatment has to be the same, and the control has to be the same if you are looking at trials or like looking at comparative effectiveness between two interventions. So let me go through the key terms that we use in conducting an analysis. So the effect size is an estimate of direction and magnitude of treatment effect. So this is something that you compute in your data table. Odds ratio is the probability of an event occurring divided, so the ratio of a probability of an event occurring to that of a probability of event not occurring in a group. Relative risk is the ratio of risk among the exposed and the risk among unexposed. A fixed effects model, this model assumes that each included study estimates the same treatment effect. So this is only conducted when we have a rather homogeneous set of data. Now, random effects model assumes that each study included estimates treatment along a range of values. So the treatment is not essentially so it can have like, so these are like the unequivocal measure estimates I was talking about. So it can rule to the treatment not working, or the treatment working, or the treatment being unequivocal with the counter or the control used in the study. So what are effect sizes? Effect size is basically unique to meta-analysis. It's a standardization required for treatments not measured in the same unit across studies. Although, to be fair, the effect size can be the outcome if your outcome estimate is the same. So if all your studies have an OR or an RR between the treatment and the control, then you can use that to compute, to run your statistic. Now, the effect size depends on the type of, but most of the time we cannot find treatments that are, so we can find enough studies with the exact same outcome estimate. But also, I forgot to mention before, meta-analysis can be conducted with 2 or more studies. So you can actually conduct a meta-analysis using 3 studies. So that's why, that's a good thing about having a stringent criteria, inclusion criteria. And that meta-analysis actually allows you to, this methodology actually allows you to conduct the study despite a very small sample size. Well, of studies, not people. Sorry. So there are different, so 2 basic types of outcome variables are dichotomous and continuous. So the dichotomous variables are usually estimated. The effect of effect in dichotomous variables is usually estimated in odds ratio or relative risk, because you have like the event occurring or not. And continuous is measured through standardized mean difference, which is Cohen's d, and unstandardized mean difference, that is like the mean difference between pre-exposure and post-exposure, our mean difference in the case versus control. So that's like a simple mathematical mean difference, and a correlation coefficient. And the correlation coefficient, as you would know, is also used in systematic reviews. And it can be deduced from a t-statistic, an F ratio, or a chi-square statistic. We are not going to use correlation coefficient as an effect size in our example today, but it's good to know that you can have this as a fallback. And there is a continuum of decision around a correlation coefficient. A correlation coefficient of 0 means no effect, and correlation coefficient of 1 means perfect effect. And those of you who have not conducted systematic reviews, a correlation matrix is a required part of a systematic review, where you actually correlate the study outcomes, the different studies you include in your research. You actually conduct a correlation matrix between the outcomes, and you kind of stack them on which ones actually have a positive correlation, which ones have a negative correlation, and which one doesn't have a neutral correlation. And from that correlation matrix, you actually deduce the evidence from the treatment. So a forest plot is an essential part of a meta-analysis because it's a visual summary of your analysis. It does not only apply to meta-analysis. You can conduct a forest plot with your outcome data in your from your correlation matrix, not a correlation matrix, but a summary, like mean and confidence interval table from your systematic review. But it actually also helps you decide whether you want to do a meta-analysis or not, or whether the data supports a meta-analysis or not. So it shows the variability in the studies, the magnitude and effect of the effect sizes, and it gives you a kind of a visual snapshot of whether the data is homogeneous, so that you go ahead and conduct your meta-analysis, or you select the model to conduct a meta-analysis, or you actually do not want to conduct a meta-analysis. Usually the data is very heterogeneous, as you can tell. It's very intuitive. A meta-analysis is not the best method to provide evidence, because you won't get, well, a very reliable summary estimate. So these are two examples of a heterogeneous forest plot. The first one has the test statistics that help you decide on heterogeneity. For example, here you have the chi-square and the I-square statistic. I-square is 92%, so that is very highly heterogeneous. I will come to the test statistics in the next slide. But this is like, but then this slide provides you with an idea of how to deduce whether the data is heterogeneous or not. So both are heterogeneous, as you can see. There are clusters of data in these both these studies. So I'm not going to talk about subgroup analysis here, but when you see data clustering like these, then you can do a subgroup analysis of the clusters to find a true effect, because your true effect might be hanging with certain parameters that were included in the studies that are hanging together. So you have some evidence as to the effectiveness of the treatment. The subgroup analysis requires like a meta regression. You actually just use a linear regression of the outcomes and see what a linear or ordinal regression, depending on your outcome variable, to see what the odds of the treatment is against the control. Any questions so far? Okay, so I'm going to go ahead and talk about the tests, the statistical tests that I showed you in the previous slide. So there are several tests that we conduct to measure heterogeneity and make a decision for running a meta-analysis. So a Cochrane's Q statistic is the weighted sum of squared differences between the observed effects and the weighted coverage effect. It's not a direct measure of heterogeneity. I'm not going to go into details of like explaining what this means, but this is like, if you have this with you, you can actually conduct the meta-analysis yourself if you choose to. So here, the detection is for a particular degrees of freedom. So it depends on how many studies you have included. So the degrees of freedom is a number of studies minus 1. So depending on the degrees of freedom, you have to find out the critical value at 95% from a chi-square chart, from a chi-square table. So you have critical values at 0.1 through 1. And we usually go with alpha at 0.05, which is 95% CI. Then we have the I-square statistic. It is the proportion of observed variance that reflects real differences in effect sizes, and it's expressed as a range from 0 to 100%, which makes it very easy for us to make the detection. So we have an arbitrary threshold of 50%. So less than 50% means heterogeneous, and more than 50% means, more than 50% means heterogeneous, less than 50% means homogeneous. So approaching towards the 50% mark kind of gives you an idea that the study might be, your sample or the data might be heterogeneous. So you need to select a random effects model rather than a fixed effects model. Now, the t-square statistic measures the dispersion of true effect sizes between studies. And again, we don't use it exactly in as an indicator, but we use it to compute weights assigned to random effects model. And these are only, there's a t-square and t. You have to compute these only if you go with the random effects model. The tau, the t statistic, which is called tau, is an estimate of standard deviation of the distribution of the true effect sizes, and it's used to compute the prediction interval. So around the combines of the true effect of the intervention, which you deduce by conducting the meta-analysis. So again, the t-squared test statistic and the tau are only used when you go with a random effects model. In the real world, it's usually always a random effects model. Data is seldom super homogeneous to actually run with a fixed effects model. So here is the promised Excel spreadsheet. So here is the actual data sheet. This is a sample data that I got from a publication, and I will share the name of the publication with you if you need to, if you want it. So I haven't. So this is sample. So here, instead of study, instead of the numbers, you need to put in your author year information. And with regards to the study design that was included in this data, it was retrospective database analysis, and which had number of events happening in the sample. And the outcome we calculated was a rate. So a rate is the event happening by the total number of people. Simply like this divided by this. So before I proceed, I have to show you the legend, and you have this in your. So I attached it to the invitation. So if you want to use this sheet, you're more than welcome to. This is actually embedded in the PowerPoint slides. But I need to go over the legend before the scheme of the colors. So this is something, the yellow columns, or the table where the column headers marked in yellow are the ones that you need to change. The rest you don't need to if you want to conduct your own data analysis. So, and these could be different. So you don't have, if you don't have events and sample size, you can do an OR. So if you have odds ratios, for example, that will be your outcome. You don't need these two, okay? And then your K is your sample of number of studies, and the degrees of freedom is K-1, and this needs to be changed as well. The blue is a calculation for a fixed effects model. So here, with the assumption that the data is homogeneous enough so that we know that we can get a fixed estimate of intervention effectiveness. And the one in saffron, I don't know what this color is. This is a computation for a random effects model, which assumes that the data is heterogeneous, and that the outcome would be distributed along a range of values. And I have actually put in the formulas here, the Excel-based formulas for each column. So we have events, sample size, outcome. This is standard error. This is variance. This is the weight. This is the weight times effect size. This is the weight times effect size. This is the tau of the study. Sorry, not this one, but this is the tau, because the tau is only applied to random effects. So, and there is attached to the sheet, attached to the PowerPoint, we also have a sheet of formulas. Those are handwritten. I'm sorry, I didn't have the time to actually type it up. So if you go back to the slides, that will be the last slide on the deck, which has handwritten formulas that are used in the computation. And in this Excel spreadsheet, these formulas are actually embedded as Excel functions. So all you need to do is put in your values here, your outcome variable values here, and then everything will be computed for you. Now, if you have more than 10, of course, you will need to put in more rows here and change your K and DF. So I'm not going to run, so the calculation is pretty simple. So I just put in the events and the sample, and then everything got populated. I'm going to show you the detection of heterogeneity here. Before that, we need to summarize the weights and the taus to actually compute the Q and I square that gives you the determination of whether you should go with the fixed effects or random effects. So Q and I square is what you compute before you make this table. Here in our study, our Q is 17, which is greater than 16.92. The critical value for 9 DF at alpha 0.05. And the T square is 49%, so it's moderate heterogeneity. So we make a decision for a random effects model. In a random effects model, you have to compute the weight separately, because the basis, the assumption of the model changes here, right? Because your outcome is not a singular outcome. It's over a range. The formula is given here, and the formula, the actual constant, the actual formula for the constant is shared in the formula sheet. But this is the constant, and you basically apply the same methodology as you applied for the fixed effects on the random effects table, and you get the necessary estimates. From these estimates, we calculate, I calculated the ES for the fixed as well, but we are not using this. We will use the random effects estimates for our plot. So we have an effect size of 0.19. This is actually the total model effect size of the intervention. This is the summary effect size that we were talking about. Then we have to calculate the standard error of the effect size to compute the confidence interval around the effect size. And this is what is required. This is like the basic statistic for your study. This is your primary effect of the intervention, and this is the confidence interval around that estimate. That is it. That's your meta-analysis. Now, we sometimes add everybody adds a forest plot for visual analysis and visual display. And this is how you, so you can see the second tab, right? Forest, saying a tab called forest plot. So here we basically copy the outcome and the standard error tables. Now, with the standard error, I copy the standard error because sometimes you don't have the upper limit and the lower limit of your outcome measures in your, so you don't have a confidence interval around your outcome in the publication, so you have to compute the upper and lower confidence interval, which you can do from the standard error. Now you just put the outcome and the standard error. I have copied the confidence interval. So basically the authors of that paper, they copied the confidence interval of their study estimates from the publications themselves, but you can compute it yourself. And then you put the outcome, your random effects model estimate here, and here, and then you compute the standard. So you've also had the standard error from the previous page. You put the standard error here, and then you put the confidence intervals here. Now so in order to get the forest plot to have the total effect at the bottom of the forest of the plot, you need to reverse the numbering of the studies. So the total effect is given a new number, study 1, and then so on and so forth. So there are several ways to compute forest plot in Excel. I am not an Excel genius. I don't know any of these hacks, so I had to reorder the data in this graph table in order to get this forest plot. So basically what I did was I have a study variable, a study column, a description which has the rate, which is our outcome variable, and what goes in the X and what goes in the Y. So the X will have your effect size, your lower confidence interval, and your upper confidence interval. And your Y will have the new study number assigned. So here I'm going to show you, I don't know if this will let me do it, but can you see me operating the Excel spreadsheet to create the graph?
Yes.
Great. So here, I know you might have a better idea on how to do it, but then you just basically, I'm showing you how I figured out how to do it. So this is a scatter plot, and you select data, you add a value, a series name is this, then X, literally this, and Y, literally this. And you see already you have a scatter plot coming along. So you have this. So this is your first, and I'm not going to repeat the whole thing, but I'm going to, so if you have to add, keep on adding, then again, select data, add, and I'm going to add the first one. So you have your forest plot here. So I just used the last study, sorry, the first study and the combined effect. So how can you deduce what the magnitude and effect of deduced from this forest plot? Like how can you tell if the intervention was effective or not? So we have a critical value of 1.0, but our confidence intervals are actually, they don't cross 1, other than study number 4. So now even with study number 4, it does not cross 1. So they are towards the left side of the the critical value of 1, which means that all the studies favor the treatment. They show that the treatment is effective. Now, this is the overall estimate, which shows that the effect was 0.19. The effect was small, but the confidence interval is very tight, so it's statistically significant. As to the other studies, like for example, study number 2 is a very long, very wide confidence interval, so it does not provide a very good evidence. But most of these studies actually provide pretty decent evidence, and our overall estimate actually shows like the overall. So the 3 has the most compelling evidence, and it's very close to, as you can see, very close to our overall estimate. But this is probably what the estimate from study number 3 probably is what made the confidence interval of our overall estimate super tight, and gave us good evidence on the treatment effect. So that is it on my side. Do you have any questions?
So you mentioned earlier a software program that you use called Comprehensive Meta-Analysis. Is that available for faculty and students at ATSU?
No, it's not, as far as I know. But if there are enough people interested, I can bring it to our institute's director's notice, or approach IT. They have $11,000 for software purchases, and we can potentially get individual licenses for the software. But yeah, if there is interest, please let me know. If you have enough people interested in conducting meta-analysis. And yeah, it's easier with CMA. There's also a free one called RevMan. I don't know if it has been updated or not. Yeah, of course. Dr. Kumar actually talked about it, mentioned it. So with the software, it becomes easier to conduct the analysis. I won't lie to you, but with the Excel spreadsheet, this method, you actually can walk through the steps of how the data is being processed and what comes off of it. So it was a learning experience for me too. So I'm grateful for this opportunity to present to you this methodology. Any other questions? Well, if that's all, I mean, hopefully it was clear and concise and of help. And if you have any questions, you can of course reach out to me. And if needs be, we can get the CMA, the comprehensive meta-analysis people to come and give us a presentation on their software. So let me know if you want that, like we did with NVivo. So anyway, so I'll give you 20 minutes of your time back. Thank you for joining us today. Those of you who need a recording, please let me know. Thank you.